Okay, so now for the main talk, we have coming to us from Krakow, we have Andrzej Sitarz from the Jagiellonian University, and he will speak about geometric spectral functions.
Okay, thank you very much. It's a great pleasure to be here on this wintry day. I hope to come one day, when it's sunny and, warm. I want to give you, so thanks also to the Ponchit, for giving an introduction in terms, saying that there are some beautiful things that extend the realm of what we work with, differential operators, to something very special. Why special? Because, what we like, and also, as algebraists like it, to have an algebra in which something unique exists. And this is an algebra on which there exists a unique trait. And why is it very nice? Because, it's very nice because the trace gives you a number. So it gives you something, tangible. And this is what, also in physics, what physicists like very much are not, the, so to say, abstract nonsense formulas. They like numbers. So in physics, physicists like numbers. And this is the way to get numbers. So getting numbers is really important. But of course, getting just a number is nothing. So the interesting thing is to, make these numbers work to get some information about geometry. And this is what this talk is about. So the basic idea is to work with something that has been proposed in non-commutative geometry. Can you block this?
Yeah, different person.
Oh,
Just,
yeah.
Running out his name, I don't recognize.
That's the thing, that's it's when some people are, up to Zoom bombing, they would be so you can make this whatever, the waiting room, right? Yeah, with Joshi. Yeah. So, okay. So coming back, this is the idea, how to replace something like manifolds in the language of non-commutative geometry. And that's an idea that's been proposed by Alan Kohn many, many years ago and put to work in, let's say, many different examples. And the idea is to give a notion to things that we use in geometry, like the differential calculus, like the metric, like the connection and all the things, sort of, I wouldn't say, general, but encompassing, all possible examples. All possible, or at least many possible examples. And the idea is to use spectral tuples. Why the notion spectral? And the spectral, because it's very, very close to what one can be considering as spectral geometry. So looking at the geometry through the spectral properties of some object, like of operators, like the Laplace operator, the Dirac operator, or just the algebra. Now, the spectral tuple, I might write something here on the blackboard. It's a very simple object. It's just, you have an algebra, which, it's not a C-star algebra, but the idea should be that it's an algebra that's dense in a system algebra. What it could be, best, it shall be an algebra of something that replaces, that corresponds to smooth functions. And of course, this is the plane, between the algebra and topology. Because when you play topology, well, what you usually use system algebras. When you play pure algebra, well, use some basis. So you look at the algebra as a vector space and you use some basis, use some generators and relation. So basically use some polynomials. So non-commutative polynomials. And this is to be something in between. So something that's bigger than the polynomials, but not C-star algebra. So not really continuous things, so not topological. Then the second ingredient in this spectral triple is that you don't look at the algebra in an abstract way. You rather look at, I mean, using Gelfand-Naimark as a represented on some Hilbert space. So you identify the algebra as bounded operators on some Hilbert space. And well, we know that each C-star algebra could be interpreted, could be seen as bounded operators on a Hilbert space. So we just use this picture. And then comes the third ingredient, which is the Dirac operator. And of course, I mean, classically, when you have a spin manifold, even spin C manifold, which is, and I like very much, you know, to repeat after Paul Baum, probably read here, I mean, in Warsaw, I mean, Paul Baum saying, you know, spin C is what you basically always see. So it's I mean, when you encounter a manifold, I mean, the chances that that is not spin C, of course, there are some examples of manifolds that are not spin C, but most of them are. So this is like a typical thing. So this is like a typical data, and this typical data, I mean, works very nice classically. And even it works for all the Riemannian manifolds for a very simple reason, and this I will give, because, I mean, of course, classical examples would be the algebra of C-infinity functions over a manifold. Let's take unital algebra. So let's take compact for simplicity closed, so no boundary manifold. You take square summable sections of the spinor bundle and just the Dirac operator. That's one example. But equivalently, a very good example of a spectral triple is the following one. You take, well, as an algebra, C-infinity functions of M. That's very nice. But then you take square integrable sections of the differential forms. So just all the differential forms, you just extend it to the Hilbert space, taking the Hodge star, using the Hodge star for the scalar product, you extend it to the Hilbert space, and you take all the differential forms. So the sections of square summable sections of all the differential forms, and you take D plus delta as a Dirac operator. So we call it Hodge-Dirac operator. This is just D plus Hodge star, D, Hodge star. But in a way, I mean, you can write this as D plus D conjugate. So just the Hermitian conjugate of the exterior derivative with respect to this structure of the Hilbert space. And this is a very good spectral triple. So technically, I mean, all Riemannian manifolds are inside. All right. So the good question is, having this data, what information can you really extract? And what information, I mean, in terms of geometric information? Because, I mean, when you look at it, so when you look at a manifold Dirac operator, and when you look at the, say, metric, so because you're looking at the Riemannian manifold. So when you have a metric, you can have, well, the Hodge star, of course. You can have the volume element, and you can compute, for instance, what's the volume of the manifold. That's one thing. Second thing, of course, if you have a metric, you can compute what's the Levi-Civita connection, take a square, compute what's the Riemann tensor, what's the Ricci tensor, what is the scalar of curvature. So that's doable. So the question is it doable just looking at that? So forget we know, well, we of course, we know what the metric if we know the Dirac operator. But can we say something about the volume of the manifold or scalar of curvature or some other object just using this data? And it appears, yes, we can. How? Well, using, for example, a technique that comes exactly, you know, from the heat trace expansion. So just looking at the operator, which is, well, say, Laplace operator or the square of the Dirac here. So Laplace operator is sort of square of Dirac plus, so square of Dirac is Laplace operator plus something. So this plus something, I mean, could be, I mean, ignored at the moment. But basically, if you look at it, then you can look at the following things. So e to the minus t delta, for delta is the Laplace operator on a manifold. It's an operator on this Hilbert space, and it's a trace class operator. So you can just take trace of it. Why it's a trace class operator? Well, we know how the eigenvalues of the Laplace operator grow, and we know that if you take the exponential, that would be a sum, give you a summable series. So you can just take the usual trace. This is well-defined trace over the Hilbert space. And then when you look how it behaves with respect to t, then, okay, yeah, then you will find that it for the manifolds, it will have the following expansion. So it starts with minus d over 2. So it has some parts which are, let's say, negative powers of t, because of course this is, when t goes to 0, it explodes, because that would be like taking trace over 1, right? So it explodes, and you can make some sort of this expansion in the powers of t. Actually, fractional powers, I mean, half powers of t. And the first part will be t to the minus d over 2. And there will be some coefficients, numerical coefficients, because this is a number, so it will be just numbers. Numerical coefficients which depend on the geometry of the manifold. And, well, that's been known since the early days that, for instance, I mean, if you look at the first term here, it will be something which is proportional to the volume of the manifold. And this is known as a Weil formula or Weil law or whatever. Now, you can ask two things. So what would be the next order coefficients? So for instance, I mean, this is expansion in n. So what would be n being 1? What would be for n being 2, right? And it appears for n being 1, that would be 0 for the compact closed manifold. But for n being 2, so the next term will give you the information about the scalar of curvature. And that's quite well known. Now, using heat trace, so computing traces over Hilbert space, even in this case, I mean, it's sort of quite annoying and might be difficult. I mean, because I mean, computing trace is just, making some sums, and the sums might not be easy to express. But there's a nice tool, using some transforms, one can relate those coefficients. So those coefficients, those heat kernel coefficients, so those things here, right? Okay, to the Wojcicki residue. Why? Well, we use the Laplace operator. Well, the Laplace operator is a differential operator. Then, from what Diponchit was saying, I mean, this class of differential operators sits in a bigger algebra, which are pseudo-differential operators. And it appears that if you take the inverse of the Laplace operator, the inverse of the Laplace operator, or any negative power of the Laplace operator, and actually, Laplace operator to the minus d over 2, is a pseudo-differential operator. And this pseudo-differential operator, well, it sits in this algebra of pseudo-differential operator, and you know that there is a trace on it. And this trace is Wojcicki residue. And one can actually, using certain techniques, relates those coefficients to the Wojcicki residue. Absolutely not related with that would be just to look at the Wojcicki residue. So we can ask, forgetting about where it comes from, heat trace expansion, all that, this was like historical, what would be the Wojcicki residue of, say, Laplace operator to certain powers? And this is, where we can get the information. And what do we know? Doesn't work. Oh, sorry. Oh, yeah, this works. What do we know? That if we take a function and we'll try to compute something where, for simplicity, we take an even dimensional manifold just to avoid square roots, I mean, doesn't really matter that much because Laplace is a positive operator, so no problem. Laplace operator is positive operator, but just, for simplicity, we avoid square roots. So let's look at the following thing, and let's treat it as a functional. So you take a function, and you just take an operator, which is a pseudo-differential operator, which is f times, Laplace operator. Where is it? Okay. Laplace operator to the power minus m. That's a pseudo-differential operator. And you take Wojcicki, so this unique trait of it. Now, what comes as a result? It comes, well, you can say something that gives you the density of the volume. Why? Because f is a function. It could be any function. So you can localize the function around one point. Localize means make it, so say compact support, and this compact support is small enough. And you can make the support smaller and smaller. So what you basically get, you get the information about the density of the volume. So of course, if you take f being 1, you get the volume of the manifold. Well, this is a coefficient, right? The coefficient, this is the volume of the n-dimensional, so Vn is the volume of the n-dimensional sphere. But it's just, I mean, yeah, that's just a coefficient there that comes here. Now, you can look at what are the other powers. So you take here other powers of the Laplace operator. So for example, take f to the power delta minus m plus 1. So you change it by delta, right? And then what comes out is something that gives you information about the scalar of curvature. Again, using the same argument. Well, of course, scalar of curvature times the volume density. But the information about the volume density you get from here. So in a way, what you get information about the scalar of curvature. Yeah, I mean, you can localize it using a function. So in fact, you can get the information, what's the scalar of curvature at each point, only using the Laplace operator and the spectral geometry. So using the spectral properties, so these properties of the Laplace operator. You can use it really to extract the information and to compute the scalar of curvature. And first, that's been sort of a result of this Zilli-Gilkey-DeWitt. So he traced coefficients and applying the transform to get to write it using Wojcicki residue. But explicitly, that's been done proposed by Kohn in the 90s, and then computed independently by Kalau-Walzer in general, and Daniel Kastler computed it for the Dirac operator in 4 dimensions, if I remember correctly. And the difference by the computation by Kastler and Kalau-Walzer was that Kalau-Walzer used the fact that you can choose your coordinates as you wish on a manifold. So using everything is local. So this thing in here is a density, so it's local. And you can use whatever coordinates you choose, you like. So the good thing was you can use the coordinates of a normal coordinate system. And then a lot of things simplify very nicely. Whereas Daniel Kastler was using sort of general coordinate system, not necessarily normal, and the computations are much, much more complicated. All right. So this is, the status of what was known and what was computed, also in many non-commutative cases, like the scalar of curvature for the conformal deformation of non-commutative tori, or, some certain things, for other examples. The point is that, of course, getting information about the scalar of curvature is nice, but it's not everything. What we would like to have, we'd like to have some sort of tensorial quantities. So tensorial quantities like Ricci tensor, possibly maybe Riemann tensor, possibly, say, metric also, expressing the metric, or, what are the other tensors that come to your mind? For instance, when you have a connection. This is, for example, torsion tensor. So this is one thing. How can one express it using these tools? And of course, well, one question that you can ask, okay, I mean, here we took the Laplace operator to the power minus m plus 1. What happens if we take minus m plus 2? Well, the answer is you will get something new, but that will be like another scalar quantity. Scalar means that will be like the Riemann tensor, so square of the Ricci tensor, square of the scalar of curvature, square of the Riemann tensor. But okay, this is nice. This is computed out of these quantities like Riemann tensor, Ricci tensor, and so on, but still scalar. So you cannot get anything that's tensorial. So what we propose, and this is already in the language of spectral triples, so language adjusted to non-commutative geometry. I mean, we have a version which uses the vector fields and all this for manifolds, but I mean, I will focus just because this is universal. This could be applied to anything, and I will show it in examples. So what do we propose? We propose 3 functionals, and we call it spectral functionals. These are the functionals over the differential form. So imagine you have this spectral triple. So what comes with this spectral triple? Well, with the spectral triple come differential forms. And the differential forms, the bimodular of 1 forms over the algebra is just things that's a space in operators generated by this, when A and B are just the elements of the algebra. So you take, well, the linear combinations of commutators of D with B with elements of the algebra with coefficients from the algebra. And this is, I mean, since A and B you identify as operator of Hilbert space, the assumption is that the commutators are bounded. So this is a subspace of bounded operators. Actually, there will be a bimodule, of course, over the A. So these are differential forms. So imagine you have this space of differential forms. So we take 2 differential forms, and you create the following functions. Well, what do we call the first functional metric? So you just take the Wojcicki residue, so, or in this case of spectral triple, this is this non-commutative residue. So we assume that the spectral triple is summable, and this means summable over their n. So when you take something, some power s with the real part bigger than n, then everything will be trace class. So then we know that there is this Wojcicki residue, so that there's this non-commutative residue. What do we take? We take VW, just multiply them. Remember, they are just the operators on a Hilbert space. You take D, absolute value of D, of course, to the power minus n, and you take this non-commutative residue of that. So that would be residue at S being 0, well, actually of VW, absolute value of D minus n plus S. And you take this as a function in S, and you take the residue as S being 0 with some coefficient. Well, the second functional looks a little bit stranger. You take the non-commutative residue of something which is V times the anti-commutator of D with W times D, and again D to the minus n. Equivalently, I tell you, there's one condition, I mean, when this is actually equal to each other, but in classical things, you can take something different, just swap it. The anti-commutator is acting not on W, but on V. And then there's a third functional, which we call torsion functional, which, I mean, as you can guess, I mean, it will tell you whether the Dirac operator you work with has a torsion. So it comes, whether it comes from a connection with torsion. Because, I mean, of course, I mean, the way you get classical Dirac operator is that you consider Riemannian manifold, you consider connection, which is Levi-Civita connection. You leave the connection to the spinor bundle, and then you use the Clifford multiplication to get the Dirac operator. But this is the so-to-say the Dirac operator comes from a Levi-Civita connection, which is torsion-free. But of course, you can start with any connection which is metric compatible, lift it to the spinor bundle, and get the Dirac operator. And this is, of course, not the Dirac operator, it's a Dirac type operator, which differs from the usual Dirac operator by a bounded term which corresponds to the torsion. And then, you see, what we can do, we propose how to compute it, how to compute this torsion function. So you can see why these are functionals, because they depend on some entries which are not scalar, so not on functions, but they depend on one forms. So the first two cases, we take two one forms. In the third case, we take three one forms. So you can just think that that would be like a two tensor. That would be also like a two tensor. And that would be like a three tensor. So, I mean, corresponds to what we consider as a metric, Einstein tensor, and torsion functional. Of course, I mean, when you look a priori at it, I mean, just at this formula, you have no idea that that would be the Einstein tensor, of course. So this came as a result, which I flash you in a minute. Yeah, so these are functionals. So this is actually, I mean, what you take. I mean, so it's a tensor in the sense that it's tensor evaluated on something and then integrated over the manifold. So I will give you the formula in a second. So the assumptions are just, you know, that you have a n-summable spectral triple, bimodal of one forms, and you know that there exists this non-commutative residue, non-commutative trace. There are certain assumptions for it, that the spectral triple needs to be regular, all these poles should be of the first order, of this sort of say spectral dimension, and so on and so forth. I will not go into details. In most cases, that's what's happening. And you will see, I mean, what are the examples, I mean, later on. Okay, so the first theorem is that exactly when you take spin manifold, you take two one forms, just usual one forms. I mean, of course, you represent the one forms as the sections of the Clifford bundle, right? I mean, you have this, the one form is just like the image of dx mu is gamma mu, right? This is the, use the Clifford algebra. And then the result is that for the usual Dirac operator, the Dirac operator on the manifold, this metric functional is, well, here comes a factor which is just the dimension of this spinor bundle, right? This is exactly this volume of the n- dimensional sphere, which comes from the integral over the sphere, from the Wojcicki residue. And then you have the integral over the manifold of the metric tensor evaluated on the differential forms. So this is how you can reconstruct the metric tensor using just the spectral data of the Dirac operator. So, you know, the right-hand side gives you the information of the metric tensor. And of course, this is local because these are one forms. So one forms you can also localize around the point by multiplying by some function of, you know, not of support within a certain ball around this point. And the left-hand side, I mean, is purely spectral. I mean, it uses just, you know, the Wojcicki residue, which is just purely spectral. So then you can show that this is really bilinear symmetric map. The thing is that also, I mean, if you modify the Dirac operator by adding things like adding connection, adding torsion, this will not change. Okay, but that's, you know, one of the nice results. I mean, it behaves nicely when you multiply it by the functions from the left and from the right. So generally by the algebra elements. And this is just because, I mean, that was constructed like that. I mean, actually, I mean, this is not, I mean, this pushing the B for the comma is trivial because, I mean, what you have the product VW, right? So if you, pushing the A on the other side is not trivial, but that comes from trace property of the Wojcicki residue. So, you know, things are general nice to prove. This is, also true for this thing. So if you take the Hodge-Dirac operator, this gives you the same metric. I mean, the coefficients are slightly different then because, the Hilbert space at a point as a US bundle has different dimensions at each point, but still gives you the same metric. Now, of course, you might ask, okay, if you look at it, where is the metric hidden? Of course, the metric is hidden here, right? In the Hodge star operation and in the conjugation, because this part, D, is universal. Okay, so this is for the metric. Now, yep. Yep. Yeah. It's just a product. So this is just, the metric is just very simple. And it is computable for many, many examples. Oh, yeah, that's just the composition of operators. Since we work with operators on the Hilbert space, no problem. Writing a product is just easy. It's a product of operators. V and W are just bounded operators. Okay, so the second part is, and this is why we call the second functional the Einstein functional. Because, that was actually, I wouldn't say, our surprise, but when we started computing, certain candidates for that, our intuition was that we'll get something like a Ricci tensor. But it was more sophisticated, and we get something which is actually, is also a tensor, and it's a tensor which is a nice sort of combination of a Ricci tensor with a metric tensor multiplied by the scalar of curvature. And this is the statement that if you take the usual Dirac operator, so the spin manifold and the usual Dirac operator for some metric, then when you compute this functional that was given before, just the anti-commutator D with V times W, D, and then D to the minus N, then the non-commutative trace of that, then just you get nothing else but the Einstein tensor. Well, with some coefficients, and the coefficients, are slightly different. This is 2 to the m V, sorry, V to B, the volume of the sphere divided by 6. Doesn't really matter much, the coefficient, but you get something which is proportional to the, of course, integrated Einstein tensor. So again, since it's local, you can get the Einstein tensor at each point. Now, there are two differences. So first, it does depend on the perturbations of the classical Dirac operator. So for instance, you may ask a question, okay, you make not the Dirac operator the standard, but you add some bundle and you add some connection. So what would you get? And the interesting thing is that what you would get an extra term that comes from the curvature of this connection. So for instance, U1 connection, and you get an extra term that comes from the curvature of this connection. What you can ask, is this the same for the Hodge-Dirac? Yes, this is the same as for the Hodge-Dirac. So for the Riemannian manifold, if you have Riemannian spin manifold, just Riemannian manifold, both things, you can use. And still, since you use the same metric, a priori it was not, of course, known that it's the same, but you will get the same Einstein, which makes sense. So this is, so say, self-consistent. Now, there's one tiny remark. It's not always a tensor. So it's a tensor, from what we know, it's a tensor only, classically, if a Dirac operator is torsion-free. If Dirac operator has a torsion, then there will be then this functional will not give you the Einstein tensor, will give you Einstein tensor plus some terms which are not tensorial. So that they would depend on the covariant derivatives of, say, W. So, not tensorial in the ways, not linear in V and W. I mean, that would be tensorial, I mean, as sort of transformation of coordinates, but that would not be linear in VNAP in this way. So this is just a side remark. Now, the third functional, which I like very much, and this is interesting. Why? Because you see, I mean, when people start considering, you know, linear connections and want to do things, I mean, for instance, prove to the existence of Levi-Civita connection, right? Well, they say, okay, what is torsion? And there's an algebraic picture of torsion and so on and so forth. But of course, you need connection for that. And you need differential calculi. And you need how to have two forms, I mean, to define the torsion. Now, in this approach, and there are different approaches. There are even approaches based on this, on spectral triples. I mean, but you probably know paper by Bram-Mesland and Ara Moreni. The point is, when you start with the Dirac operator, abstractly, satisfying certain axioms, like, for instance, you have the Dirac operator for, say, SUQ2 or for the non-commuted torus. How do you know that this Dirac operator has no torsion in it? I mean, classically, when you consider space of Dirac operators, there are some Dirac operators which have torsion, there are some that don't. Classically, you don't see it in the differential calculi. Differential calculi are the same, but non-commutatively, you will see it in the differential calculi. So, you know, there's some sort of a mix-up. So what do we have now? We have some tool to tell us whether the Dirac operator and the spectral triple has, what do we propose? Torsion zero Dirac operator, so no torsion. And the condition is very simple. So the condition is just that you, well, compute this functional, and remember this functional is very easy. This is just, you know, well, sorry, okay, it's very easy. It's just UVW, product of three one forms, D and D to the minus N, and you compute the residue of that. And the statement is that if you do it classically for the spin manifold with the Dirac operator, then what you get the torsion coupled to just contracted with these three forms. So this is a three tensor. And actually, if you look at it, I mean, the only Dirac operators for the spin manifolds can come from the torsion that are self-adjoint, can come from a torsion which is totally antisymmetric. So this totally antisymmetric part of the torsion, and this is what's computed here. So it gives you just exactly, and you can say, well, the Dirac operator had no torsion if this is equivalent to this functional being identically zero. So you can just, you know, extract it. Now comes an interesting thing. I mean, if you look at it, you might think, come on, how can we say something about torsion? There's no connection here. I mean, this is constructed just giving the metric. No connection somewhere in the background, right? So you may ask a question, what's the torsion here? And well, this is not absolutely evident, but I mean, you can write this operator using connection and using actually Levi-Civita connection. You can write this operator using Levi-Civita connection. This is not a commonly known fact, but that's the case. And you can compute that the Hodge-Dirac operator has no torsion. We computed it, and it comes out, I mean, the torsion vanishes identically, which is an also sort of, I wouldn't say in a deep, but absolutely non-trivial result. I mean, when you ask it to the people, I mean, would this operator be torsion free? I mean, that would be not a, let's say, immediate answer. Okay. Now, the proofs in the classical realm of manifolds, I mean, this is what Ponchit was talking about. They use the pseudo-differential calculus. So basically, the tricky point is to write the inverse of an operator as a pseudo-differential operator and just The rest is computing the Vojicki residue, which is also non-trivial but possible. So I will skip the proofs. And of course, the good part of that is that we use normal coordinates. And why we use normal coordinates? Because in normal coordinates, you can make the basically expansion around the point. So you fix a point on the manifold, you introduce normal coordinates around it, and then you can write very nicely the metric around it. So that simply means other language, you can say, I mean, the metric at this point in this coordinates is just the Kronecker delta, and the derivatives are given by the Riemann tensor. The same, well, you can write about the determinant and so on, the covariant metric, contravariant metric, everything could be written very nicely, and that makes the computations, well, easier. So, for example, I mean, if you just, write what is the symbol of d square, so the symbol of d square is just the psi square, so the psi coordinate of the pseudo differential squared plus terms which are O of x, so depend at least on x. So it simply means they vanish at x being 0, because you choose coordinates such that the x being 0 is the point on the manifold. Everything is local, and so on and so forth. So, for instance, for the Dirac operator with torsion, I mean this is the symbol of order 2. This is the symbol of order 1, which has this torsion term, and then you can write what are the symbols of the inverse of the d to the power minus 2m. So this is d to the 2, this is d to the minus 2m. And then you write two symbols like that. And then this is, just, the technique, to get the result. Okay. Final part, you go beyond the spin manifold. So going beyond the spin manifold, for the Hodge-Dirac, I already mentioned, what do you get the result? You get the same metric, same Einstein tensor, 0 torsion. What do you expect? But still, when we started, when you think of it, now it's maybe for us, it's sort of obvious. But when you think of it, it was not. But then, how can we go, to more interesting stuff like non-commutative? So first thing, you just take the so-called non-commutative torus, two torus, which with conformally rescaled spectral triple, which means the following. So you take the usual algebra of non-commutative torus. So UV is e to the I theta VU. So just the deformation of usual non-commutative torus. What do you take as an algebra? Well, let's say, sin infinity functions of this non-commutative torus. Then you take the Dirac operator. Well, the Hilbert space would be just the L2 of that tensor C2, so 2 by 2, by 2 copies of that. This will be like H D flat H, where H is actually not in the algebra, but it's in its commutant. Why? In a commutant, the commutant of the non-commutative torus is also a non-commutative torus. So basically you can, this is not from this algebra, but from an algebra which is sub-opposite. Why we take it from a commutant? For a very simple reason. It changes the Dirac operator, changes the spectral triple, but still the commutators are bounded. We don't need to go to what people do with twisted spectral triples. Don't want. So now, when you just have it like that, you can compute what's the metric functional, and the metric functional comes just, sort of natural, computing the metric, and you can compute what's the Einstein functional. And the Einstein functional comes identically 0. Does it make sense? Yes. For any two-dimensional manifold, the Einstein functional vanishes. So the Einstein tensor vanishes for two-dimensional manifolds. So this makes absolutely sense. And this is, sort of non-trivial computation. It's actually sort of easy in this case, but it's really non-trivial. And this is, something that, well, we can say, this conformally rescaled non-commutative torus is an Einstein manifold. It should be like that. Okay. Now, a little bit more harder. So let's think about a 4-dimensional non-commutative torus. I mean, it would be sort of surprising. I mean, if then it comes as 0, it would be stupid, right? I mean, it would mean that we're computing, you know, a lot of zeros and nothing else. But then, if you compute it, well, I mean, I used K, not H over there. Depends on, you know, which paper you look at. People use it differently. Well, you have the correct rescaling for the metric with this K. So if you look classically, that should be like the classical K is just a function. And then you have a expression with a lot of K's, derivative of K's, and so on, so forth, K inverses for this Einstein tensor. Looks complicated, but you know, it's not is a formula that fits on one slide. If you look for the formulas for the scalar of curvature that some people get, if you know the papers by Masoud Kalkali and the others, I mean, then the formula, I mean, spans like 3 pages and you cannot read anything of that. So here, look at it. I mean, this is tangible. And if you take the classical limit, so commutative limit, you'll be surprised, but you get the correct result. That would be the Einstein tensor for the 4-dimensional conformally rescaled torus. So that was just a check. Now we sort of generalized one thing. So this condition with spectral torsion vanishing, we generalized to something which we still don't have a very good name. We use something spectrally close, which is sort of generalization of no torsion condition. And this means basically, I mean, what you can add to the Dirac operator, well, you can add torsion. Torsion starts with dimension 3, right? There's no non-trivial antisymmetric torsion tensor, 3 tensor in dimension 2, of course. Starts with dimension 3. But you can add to the Dirac operator things that could be, so in 5 dimension, for instance, you can add something that's sort of a dimension 5 tensor. 7 dimension, you can add 5, 7, and so on and so forth. So there will be generalization that there are no such terms. And we call it spectrally closed. So spectrally closed. And this is more general than torsion. It implies no torsion. And it just tells you that there are no extra terms in the Dirac operator. So classically, it would tell you that the Dirac operator is the spin Dirac operator. Now, what are the examples? So we ask ourselves, what are the examples of no torsion geometry, which are, they'll say, mildly non-commutative. So the first thing we looked at is the Yang-Mills. So you take the spectral tuple, which is just, you know, you can say it matrix valued infinity function. And you take the Dirac operator, which is just the diagonal Dirac operator. So it acts, the usual Dirac operator acting on, let's say, each component of the Hilbert space. But then it has some connection. I mean, you can view it as some connection. This has been just, this A is an homomorphism of a band. Sort of fluctuation. So it's a matrix value endomorphism of the band. So it's both an endomorphism of the spinor bundle and of the endomorphism of this another band. And then, well, what we just computed that this example has no torsion. You can compute what is the Einstein tensor of that, and becomes this curvature, but it has no torsion. Second, this conformally rescaled non-commutative torus also has no torsion. It's actually even spectrally closed. So it's even better for any n, actually. So this is nice. This is something what we would expect. Why? Why it is important? Because I mean, if you, for example, well, if you rescale the Dirac operator in this way, this gives you no torsion. But imagine you start not with a Dirac operator, but with a Laplace operator. And you rescale Laplace operator like that. This will give you torsion. So the message is that such Dirac operator is the Dirac operator without torsion, but this is equivalent to the Laplace operator for a connection with torsion. So this is something different. So that was not obvious. And then, the example that I will want, to look at, and which is very nice, which is just SUQ2. So SUQ2 is the, canonical example of a quantum group, and the most studied example with all the differential calculi known, a lot of things known. So besides that, there is a spectral triple on that. So-called isospectral spectral triple. So the spectral triple where Dirac operator is the canonical, it's the same Dirac operator basically as for the SU2. Now, of course, the Dirac operator is the same, but the differential forms are different because the algebra is different. So the differential forms are different. So the question whether this Dirac operator is torsion-free is absolutely not obvious. So fortunately, all the things, using the usual basis, this Dirac operator could be written in a canonical basis of the Hilbert space orthonormal basis. Also, the representation of the algebra could be written on that. And the non-commutative residue is computable. It's just computable on this Hilbert space. There, you can write this, so you can rewrite it using certain functionals over the algebra. So abstractly, you see, for this geometry, you can compute things. So these functionals are actually computable on the differential form. And that's what we did. We just used this algebra, the representation, so this canonical spectral triple for that, compute the torsion function. And, well, you can say surprise, surprise, or no surprise. It came out as 0. So this operator, so this spectral triple has no torsion. Now, you may ask, can we have a torsion? Of course. This is three-dimensional thing. So the nice thing about this spectral triple is that it's dimension 3. So you can ask a question, okay, how can we get a torsion in dimension 3? Well, torsion dimension 3 is a totally antisymmetric 3 tensor, so it basically amounts to a function. So if you want invariant function on a SUQ2 or SU2 as a constant. So if you add a constant to this Dirac operator, it will give you torsion spectral triple. And you can compute then the torsion. Just you can see what distortion is. So this is a nice example. These are examples where there was no torsion. Well, there is an example when you can have torsion. And funnily enough, this is an example using, well, this conlot model. This model of almost non-commutative geometries. When you take a, so say, the manifold you consider is a product of something which is usual manifold with something which is discrete, finite. So in this case, Z2. And if you take the standard Dirac operator is just the Dirac operator with some, this could be function. We took it as constant. Chi is the chirality. Phi is just a complex constant. This Dirac operator. The algebra is just, functions over the manifold and over 2 points. So tensor C squared. This, you double the Hilbert space and take the Dirac operator as a matrix. Then what you can compute that the torsion part of this Dirac operator, also the torsion functional, comes out as proportional to the volume functional or the metric functional with this phi squared. So you can, if you're using this interpretation, this is like a Higgs field. So actually, you have the interpretation that Higgs field could be considered as a connection, but it could be considered also as a torsion of something. Doesn't really make any difference because this looks like something as a question of interpretation. All right, what's the outlook? So what can it be used to? Well, study torsion Levi-Civita connection. So once you have a Levi-Civita connection, for something and you try to construct a Dirac operator, then you can check whether this definition of torsion gives you 0. Equivalently, when you have some connection and you don't know, for instance, whether, or you have some Dirac operator, you don't know whether it's related to something torsion-free, you can check whether the torsion function vanishes or not, if it's computable. Most cases it will be. There are some questions, how it relates to the quantum metric spaces. So the question of distances on the space of functionals, right? So on the space of states. So this is the question, you know, on this compact in this quantum metric spaces in sense of Riffel, Latre-Molière. Now, classically, I mean, something which is open, I mean, how it goes for the manifolds and orbifolds. And also, you know, sort of non-commutative orbitals, because I mean, this is something which we observed some time ago with Tomek Brzeziński, that, you know, there are classical orbifolds, and you can actually get the even algebraic insight in those sort of singularities. But when you go non-commutative, it changes. So there are this something like the non-commutative pillow. And for the non-commutative pillow, which is the quotient of the torus, non-commutative torus, for the non-commutative pillow, I mean, the singularities, I mean, appear to, I wouldn't say vanish, but are somehow, you know, yeah, smoothed out. I mean, smoothed out maybe smoothed is not a good word, but I mean, somehow like more regular. So then there's a question of flat manifolds. I mean, you can just say what flat means. You can say what Einstein means. So this is another thing. I mean, we have, for instance, a conjecture that something like, well, of course, you know, I stress out suitably regular, because we don't know what would be the condition. But our conjecture is that the regular spectral triple of dimension 2, with some possibly maybe extra conditions, I mean, we don't know yet, has a vanishing Einstein spectral function. So that would be nice, for instance, to check it for other non-commutative two-dimensional manifolds that you know, for instance, all quantum spheres. Well, we expect that it's not only regularity, there would be something else, I think. But, you know, this is something we can have, but we can have access to something you can call Einstein manifold, right? Using this, we can have it. And I would say thank you. Hope that was, you know, something that encourage you to look at not only, you know, the algebraic part of things, but also looking at this sort of more functional, or so analytic functional part of things, can give some more information. So that's the message, that you can get a lot of interesting informations computing those non-commutative residues and computing them on a certain manner. And this might give an information which is purely geometric. And this is, you know, all based on 3 papers together in the same group with Ludwik Dąbrowski from CISA and my former PhD student, Paweł Zalewski. Thank you very much.
I'll start. And so, I mean, as you know, we have algebraic analogs of torsion, Einstein, so on and so on. But like the first, we're looking at them for quantum like manifolds, or in specific Podley sphere. And of course, then we don't have the regularity or the convergence, because of course the eigenvalues and the multiplicity of the eigenvalues don't match. So is there some way that you could extend it? I mean, just even for your example, for your spectral triple on Podley, some way to get around this.
The point with Podley sphere is highly complicated. Why? Because, I mean, when you look at this, I mean, there is a spectral triple for the Podley sphere. Yeah. I'm not very happy with that, because, I mean, this is a spectral triple of, say, dimension 0. And when you look, I mean, at the spectral dimension, then it doesn't satisfy those. I mean, we wrote a paper with Bruno Jochum on that, on what is the spectral dimension of this Podley sphere. And when you look at this zeta function of the Dirac operator, and you look at where are the poles are over, well, let's say, left to the zero at this sort of crate of some points, but infinitely many points and infinitely many up and down and to the left of the imaginary line. And moreover, I think all of them, or maybe some of them, I mean, those on this line are of the second order, and this doesn't look good for the trace. I mean, we haven't continued that.
Well, it was like the paper with Uli and Adler, where they put in twists.
Yeah, the twin.
And then suddenly everything worked.
Yeah.
So is there some way in which you could perhaps twist this?
Yeah. So this is one of the things that probably the good approach to some geometries would be not, the spectral triples. I wouldn't say twisted spectral triples. I mean, twisted spectral triples, I mean, are not. I just say in a moment why. I mean, twisted spectral triples might not be the best answer, but something which is called, I mean, it's almost like that, modular spectral triples.
Yeah. But I mean, they weren't twisted. They were taking your spectral triplet, and then they were twisting the trace.
Oh yeah. So that would be like modular spectral triplet. Yeah.
Okay.
So this is modular. You twist the trace.
That's
Exactly.
Okay.
Yeah. You twist the trace. That probably should be the answer. I mean, for some geometry, that's true. So some geometries might require an extra data, which is just some sort of. I mean, it would be like modular operator. Why? Well, first of all, to get the correct Hochschild and cyclic dimension. Yeah. So this, yes. So for the Podley sphere, that's to be done.
Mm-hmm.
The thing is, I mean, that it would be very nice, to do it not only for the Podley sphere, but do everything like that for the SUQ2, and to have this compatible, because this is the sort of problem. Because the spectral triplet for SUQ2 is very nice. It's three-dimensional, and then suddenly when you go to the Podley, I mean, either you look at this as two-dimensional with modular operator or something like that, or you go to zero-dimension, which is sort of not nice. So this probably is a way, to go a little bit more further to see it exactly as a Haupt-Galois extension. Yeah.
And probably to compare what you have analytically.
Yeah, absolutely. I mean, comparing things that are algebraic with analytic, I mean, is a huge challenge. Especially that, for instance, I mean, if you take this non-commutative torus, this conformally, there are, I would say, at least 3, 4 algebraic approaches, which, I mean, you can to compute the curvature, so say scalar of curvature. And I think, at least 3 of them give different results. I mean, different from each other. And it's totally different from what comes out as analytic approach. So the spectral approach. So you see, I mean, there's a lot of, things to match, to do.
For you, it's from Partha Nandi. In the case of a smooth manifold, geometric information is shared by the inner product of the Hilbert space and a suitable choice of Dirac operator, which reflects the curved geometry. In the context of Kahn's formulation, could the curved counterpart of the Dirac operator, involving the spin connection term, which seems to be predetermined, arise naturally within the framework of the standard model? Specifically, is it possible to unify the spin connection in such a way that it emerges naturally from fluctuations, similarly to how the Higgs connection, along with other gauge connections, arise in gauge theory?
Well, what I would say that, this, of course, the spin connection, you can say, arises naturally in a way that, I mean, So classically, when you have a Dirac operator, so Dirac operator is a differential operator. So classic. Differential operator has the two parts, the parts of the first order and the part of the zero order. And when you, the part of the first order part, so you can say it using this language of so the differential operator is the principal symbol, has the information about the metric. The zero order part is constructed in such a way that the full operator is self-adjoint. That's it. You can choose it as a sort of definition. And then when you check, when you take, okay, we want an operator that is self-adjoint and has zero torsion, then it fixes the spin Dirac operator. Now the extension, to the other bundles just tells you that the Dirac operator, okay, has this principal part which is still the same, but will have the zero part, zero order part, which could be changed by any endomorphism of the vector bundle, which is just a connection. So this is the information on the connection part. So in a way, I mean, looking at instead, I mean, this is what the idea of Kohn proposes. Instead of looking, at fixed Dirac operators or whatever, fix something, and looking at fields, you look at the space of operators. And the space of operators contains the information about all possible metrics, all possible connections, and also would be also torsional, would be also some other field. So this is, you encompass different things in one object. So one object is just a sort of generalized Dirac operator. And in this operator, I mean, you can have the data, which is both the connection on some bundle, both the spin connection and the metric. That's it.
A quick question from Partha Nandi, who is actually a postdoc at Stellenbosch University in South Africa. So he's coming from a long way away. Is the concept of a spectral triple well defined if we replace the smooth manifold with a non-commutative Lie algebra, for instance, a non-commutative space-time? How can we reconcile the concept of curvature in this case? Alternatively, is it possible to construct the concept of metric directly from the non-commutative space-time algebra?
Well, if you go non-commutative, so the concept of spectral triples is well defined for most of the deformations, but not for all of them. So, for instance, I mean, people have been struggling, to define a good to give a good definition for, say, kappa deformation of Minkowski. So there are some propositions, you may like them, you may not. For the Noyal deformation, this is well defined. But, for the Q deformations of the space-time, I haven't heard about spectral triple approach. So not all examples of deformations have a nice, well-deformed spectral triples. Actually, for quantum groups, I mean, there is an abstract construction of Tusset-Nishpeyev for all quantum groups, but it's very, very, I would say, complicated. Yeah. So not all deformations have spectral triples. Okay, I think I should be finishing and running for the past. Yeah. Yeah.
Hello, can I ask one question? Andres? Hello? Hello? Hello?
Quick, because Professor Sitarz has to run, but go ahead.
I just wanted to ask you one thing. Means in your construction, you have not spoken about KO dimension of the fluctuated Dirac operator when you use.
It will not affect metric, it will not affect the torsion functional, it will affect the Einstein functional by adding the curvature term of the connection. Yeah. Oh, remember the problem. Yeah. So shall I repeat? Shall I repeat?
It would be good if you repeat. I could not hear it.
Yeah, so the answer is that if you consider fluctuated Dirac operators, that doesn't affect the metric functional, doesn't affect the torsion functional, but it affects the Einstein functional. It changes it by the term which is proportional to the curvature of the connection, of the fluctuation that you add.
No, but my question is, means KO dimension, how does it play a role here? KO dimension space.
KO dimension.
Yeah.
I haven't considered KO dimension, no real structure.
Okay.